Hey, it's Dr. J, 6.2, part 2 of exponential functions. Today we're going to focus primarily on the graphs and then some new type of functions that may arise from our analysis of these graphs. Just to get started today, let's do a problem that we might have seen in the past. Maybe last week sometime. So let's graph the exponential function 5 minus 3 times 2 to the x. First thing I want to say before I do any of the problems, you will be tempted by your natural instinct or maybe your mathematical training since you were a child to see the operations that you recognize and actually try to calculate them. For example, 5 minus 3. Don't do it. Don't do it. If you do 5 minus 3 and you get 2, you're going to screw everything all up. Similarly, here you have 3 times 2. Don't do it. Don't go 3 times 2 and make it 6. All right. Each one of these numbers represents a different operation, and they cannot be taken out of order. They cannot be combined together. So you have to analyze each and every one of these. One thing you might do is rewrite it negative 3 times 2 to the x plus 5. I like to rewrite this so that you realize who everybody is. You want to see who is the leader and who is the base and what each and every term represents. This 5 represents a vertical shift. And when you see it written in the front like this, you might not recognize it as a vertical shift. Okay, that is a plus 5. That's a positive 5. So we are shifting the graph up 5 units. Okay. The negative 3. Yeah, that's this negative 3. It makes a lot more sense if you put it in the front. At least it's clearer to see what it is. This is going to reflect about the x-axis. In other words, it's going to flip the graph over. So flip it upside down, and it's going to stretch by a factor of 3. Yeah, so this is doing two things. It's reflecting. That's the negative, the reflector. And the 3 is stretching the graph. It's going to make it taller than it normally was. Okay. Notice that nothing is happening to the x. So there is no horizontal shift. None. The graph is not being shifted horizontally. The base is 2. That's our mother function. Review your notes from the previous lecture to get the x and y values for the base 2 mother function. I'm not going to redo all of these. These are the same x and y values from y equals 2 to the x that you look at the base to decide what mother function you're doing. Okay, so we're going to multiply all of our y values by negative 3. And then we're going to add 5 to all of the y values. And we're going to do nothing to the x's. The x's are going to remain exactly the same x's. Yeah, no horizontal shift, no horizontal shift. Sometimes refer to that as an H shift. There is no H shift. Shift. God, the more I try to fix it, the worse it gets. Shift. There we go. So there is no horizontal shift. Okay. Now remember, we only need to get 2 good points out of this. We'll probably get a lot more than 2. But nonetheless, we can fill out our new table, hoping we get 2 good points. Notice the x's haven't changed, so we're going to use exactly the same x's. Our y's are going to change a little bit. We've got -3 times 0.25 plus 5. That's going to be 4.25. 0.5 times 3, -3 plus 5. That's going to be 3.5. Here, -3 times 1 plus 5 is 2. -3 times 2 plus 5 is -1. If you have to, use a calculator, do some scratch work. -3 times 4 plus 5 is -7. Okay. One thing to notice is that these y values are getting closer to 5. As x approaches negative infinity, so for example, if I said -100 or something, or -1,000, or -10,000, etc., you're getting very, very, very large negative. Although between you and I, it's technically a small negative number, but it doesn't look very small, does it? It looks like a big negative number. What happens is f of x is getting very close to 5. It's going to be 4.999999999. It's going to be very, very close to 5. So that tells us that this 5 is the horizontal asymptote. Y equals 5. That's very important, because when you go to draw the graph, that should actually be the first thing you draw before you actually start plotting these points. So you can look at your table and you can look for a tendency. You can look for what happens as these x's get closer and closer and closer to a particular value. So x is getting close to negative infinity. It's getting very large negative. And y is getting close to -5. If you don't believe me, take your calculator and plug in, -100. That's big enough. You don't really have to go to 1,000,000. Yeah. Or what did I do? 10,000 or whatever. Okay. So there you go. There's your graph. You got your horizontal asymptote. You got your points. You really only need 2 good ones. I'm going to plot as many of these as I can get onto my board here. So the first thing you want to do is go up to y equals 5 and make the horizontal asymptote through y equals 5. Make sure you plot that first, and then pick any 2 points from this to put onto your graph paper here. So how about 0, 2? Here, let me just say 2. It's the same thing as 0, 2. And then let's do 1 and -1. So this is x equals 1 and y equals -1. And that's good enough. Yeah, that's full credit. I'll give you 100% for that. Yeah. If you've got room, you could certainly go all the way down to -7. You go over x2 and down -7. If you have a very fine piece of graph paper, you could probably plot these decimals over here. If you really want it to look nice, watch, this would be extra, extra special. I would go like this. And then at -2, I would do 4.25. Although I think I just made it look worse, but You could do that if you really needed to. And when you have a piece of paper, you can do lots of different things that you can't do with a computer. All right, so pick 2 points on canvas when you draw your graph with your mouse, okay? I don't have room here to go all the way down to -7, so I'm just going to omit that point there. I'm just going to pick those 2. Okay. I may also ask for the domain and the range. Remember, the domain is a free answer, -infinity to infinity. Try to take your free answer. The range is not free. You have to look carefully at the graph. It goes from -infinity all the way up to y = 5, but it's never going to touch this dotted line. So it's always going to stay below y = 5. Okay, so this is the graph f of x equals 5 minus 3 times 2 to the x. All right, that's where we were last week. This week we're going to turn the tables a little bit. I'm going to start with the graph, and you're going to tell me, or I'm going to tell you how to figure out what this particular equation is. So given the graph, find the function f of x equals k plus cax. And I've got a graph here pre-made for this presentation. So suppose you already have the graph. Now, I'm not sure how clearly you can see the grid lines, but each of these grid lines is 1 unit. So we have 1, 2, 3, 4, etc. -1, -2, etc., etc. Down here, -1. Up here, +1, +2. It's not necessary to label every point, but it might be a good idea to have a few of them labeled so that you know what you're actually dealing with. The first thing you want to look for is the horizontal asymptote. All right. It's either a floor or a ceiling, and it should be invisible. It's like it's made out of glass. Yeah, so you can't clearly see the dotted line. The computer will not draw the dotted line for you. I draw it, you might draw it, but the computer doesn't draw it. So you want to kind of look over here at the graph and see if you can see a ceiling or a floor. In this case, it's a floor. You can tell that it's a floor because none of the graph goes below that line. So that line is what we refer to as the asymptote. So we automatically know what k is. K is -2. This point here is -1. This point here is -2. And this graph is never going to pass -2. So that's your k value. I should just mention k is a y value. We don't say y equals -2. We say k equals -2. The asymptote is called y. I know that drives a lot of people nuts. You just called it k, and now you're calling it y. You know, can't you make up your mind and always call it the same thing? Well, it is a y value. It's a y value that's called k. So, tomato, tomato, right? All right, so there you go. You've got your k. K is done. Check. Now you want to find c and a. doesn't really matter the order that you do it, but I do find that it's easier to find C first. Yeah. And then I find A last. So just pick a point on the graph and use it to find C. So come over here and pick a really nice point on the graph. If you have the opportunity, pick the point that has x equals 0. And in this case, y equals -1. So if possible, if you get a problem that has a point at 0, pick that point. That's always going to be the easiest point to use. So we're basically saying that x is 0 and y is -1. I need a little bit of space to work here. So we have y equals -2, because we know that k is -2, plus CAX, and now we can plug in x equals 0 and y equals -1. All right. It should be relatively simple. I'm not going to give you any really complicated problems. I mean, they might look complicated, but that's just an illusion, right? Everything looks complicated if you don't know what you're doing, right? Once you realize what you're doing, you're plugging in x equals 0, you're plugging in y equals -1, and look, it doesn't look so complicated anymore, right? Remember the rule from exponentials last week? Anything to the 0 power is 1. It's not 0, it's 1. Okay, and so now solve this for C. And you're going to get C equals 1. Let's write down what we have so far. We have k equals -2, and we have C equals 1. We have one more thing to find. I always save the A for last. All right, so I got y equals -2 plus 1 times a to the x. If C is equal to 1, you may omit. Or not. You can keep it as a 1. I wouldn't mark it wrong, but you may omit it. So I assume that most of you will choose to omit it. You know, why write something that you don't need to write? It's an invisible 1. It's right there. If C is not 1, you may not omit it. You have to put it in there. Okay, that rule only applies in the instance that you get 1. Okay. Now you can't use the same point twice. So come back over to your graph and pick a second point. So pick a second point and use it to solve for A. So I picked this point here, which is 1, 2. You have lots of choices. Any point on the graph you can pick. You can't use the same point twice. So plug in x equals 1 and y equals 2. So notice x is now 1, y is now 2, and you can solve this equation for A. And there you go. You got everybody. So your answer, f of x equals k, k was first, plus c times a to the x power. Just to annotate who everybody is. That's K, that's C, and that's A. K, C, A. When you type this into the computer, you may omit the C, so you can just write it like this. So your answer is -2 plus 4 to the x power. Now don't get too carried away. I sometimes will see somebody do the entire problem right. They'll get to the final answer, and then they'll screw it up at the very end. Don't combine these together. Just put it down before you break it. If you keep messing with it, you're going to mess it all up. Let's try another one. So find the function, same basic idea shown in the graph. Be right back with the graph. Give me a second to copy the graph. I don't have a screen share option on this video, so I have to do everything this way. Okay, graph is ready. So the first thing you want to do is look for a floor or a ceiling. This one looks like a ceiling. Yeah. I won't try to trick you. You'll see that the entire graph is below a particular value. I'm not going to have it be questionable. You know, I can't tell what that is. It should be very clear what it is. The ceiling is y = 3. So that is your k value. Okay. The asymptote is y = 3. The vertical shift is k = 3. Tomato, tomato. They mean exactly the same thing. That's the easiest part of the whole problem, is finding the k. It's the only part of the problem you're going to get for free. The rest of it you have to solve for. So you got y = 3 plus cax, because you already know that k is 3. Now pick a nice point on the graph. If possible, use a point that has 0. So that's 0, 0. That's even better than last time. Yeah, you get double zeros. X and y are both 0 at that point. It's called the origin. What's nice about 0? Anything to the 0 power basically turns into 1. Yeah, it does turn into 1. The value of a to the 0 is 1. Yeah, and now you can solve this. You're going to get your c is -3. Yeah, see, 0 minus 3 is -3. Okay. Finally, pick a value that we didn't know or that we haven't used already, something else on the graph. You've got lots of choices. You can pick a point down here. You can pick a point over here. It really doesn't matter. It should be a new point. I'm going to go with this one, -1 for x and 2 for y. You could have also gone with this one down here. Looks like x is 1 and y is 1, 2, 3, 4, -5. Really doesn't matter, okay? Once you make your choice, don't change your mind. So I'm going to stick with my decision. I already know k. K is 3. I already know c. C is -3. The only thing left to find is a. So k is 3. C is -3. Nobody likes to see plus minus like that, so we typically simplify that. Plus -3 is the same as just 3 minus 3. Now again, you got to know how to put the brakes on your brain. Sometimes your brain gets ahead of yourself and you'll see 3 minus 3, and you might go 3 minus 3 is nothing, and then you've got nothing, and now you're done, right? Don't do that, right? This 3 means something totally different than this 3. Those 3's don't even know each other. So they certainly can't cancel each other out. They don't even see each other. Okay, so what did I pick? I picked x equals -1 and y equals 2. I'm trying to find a. Solve for a. So plug it in. Y is 2. X is -1. And now I'm going to solve this equation for a. Hopefully you don't forget. Sometimes you get so into this that you just completely forget what things mean. What does a -1 actually mean? Remember, it doesn't really mean negative, does it? No, I say that a lot. A negative power just means reciprocal. Yeah, so it does not actually mean a negative number. Right? We just don't have enough symbols. There isn't a symbol for reciprocal. There just isn't one. So we use a negative sign as a symbol for reciprocal. I mean, if you can come up with a better symbol and you can convince 7 billion people on Earth to switch to the way you want to do it, well, then you can be the supreme leader. Yeah, but until that day comes, you have to use the system that we've already developed, okay? So -1 means reciprocal. After that, the rest of the problem basically solves itself. Just move everything over to the other side and get your a by itself. I probably don't even need to tell you what to do from here, right? You could just follow your instincts, multiply both sides by a. So you get -a equals -3. And then divide by -1. So a is 3. Wow, I couldn't have planned it any better. Everybody came out to be a 3 or a -3. Yeah. So your final answer would be f of x equals k. K is 3. C, -3. And then a is also 3 to the x power. And so that would be your answer. It's relatively easy to check, you know. I mean, if this was the test and you think this is your answer, just come back over here and double check. If you plug in 0, do you get out 0? Yeah, well, that's pretty obvious. Look, 0. So 3 to the 0 is 1. 3 times 1 is 3. And then 3 minus 3 is 0. So it's still true, yeah. How about this one? If you plug in -1, do you get out 2? Okay, plug in -1. 3 to the -1, that's 1/3. Yeah. Then 1/3 times 3, That's 1. And then 3 minus 1. That's 2. So if you take the problem and plug the points into the answer and any of the values don't match, well, then come back down here and double check. Maybe you made a simple mistake or maybe you made a really bad mistake, but you do have that chance to rethink your life before it's over, okay? Or before you click submit. Make sure you don't click submit until you're done with all the problems. Okay, I'm going to put away the graphing board for a minute. We're just going to talk a little abstractly about mathematical relationships. A natural exponential function we're going to talk a little bit about a natural exponential. I'm not going to do much with it today. I'm just going to present it to you, give you a few examples. But then I want you to hang on to this concept, and we'll come back to it later when we start doing some more application, which everybody's probably looking forward to is the word problem section of this, where we'll solve some problems involving nature, in particular people and things that occur in nature, animals, bacteria, coronavirus. No, just kidding. Okay, so here's a natural exponential that we're going to talk about. F of x is the function 1 plus 1 over x raised to the x power. I just want to demonstrate what happens to this thing. Yeah. So we're going to let x get very, very large. Yeah, we're going to plug in bigger and bigger and bigger values of x. The first couple you can probably do in your head, but after that, you're going to need a calculator. All right, remember, we're heading towards infinity, so we're going to take some pretty big steps here. We're going to start with 10, and then we'll go to 100 and 1,000 and 1,000,000 and 1,000,000,000 and so on and so forth, okay? So let's start with 10. You get 1 plus 1 over 10 to the 10. Now, you probably could do this by hand, 1.1 times 1.1 times 1.1 times 1.1 10 times. But you know what? You're allowed a calculator, so you might as well do it. 1.1 to the 10th power. You're going to get 2.59. Let's go a little bit farther. 2.5937. Let's go to 4 decimal places. That's typically what I ask for in the homework, so you want to model that. All right. And what we're going to do is we're just going to keep letting x get larger and larger and larger and larger and see what happens. So that's 1.01 to the 100th. You will notice a pattern very quickly. 1.01 to the 100th power. 4 decimals, 2.7048. How about 1,000? 1.001 to the 1,000th power. 2.7169. I don't know if I have room for 1,000,000. Let's see if let's do 10,000. So 1.0001 to the 10,000th power. You might notice something. Look, 2.5, 2.7, 2.7, 2.7. In fact, it's 2.71, 2.71, 2.71. Let's keep going. Let's try 100,000. That's 1.0001 to the 100,000th power. You know, the first time I saw this, I just couldn't believe it, because it seems like if you're plugging in bigger and bigger and bigger numbers and you're multiplying, I mean, common sense says that when you multiply bigger and bigger numbers, you're just going to continue to get a bigger and bigger and bigger number, right? Well, common sense doesn't work in this scenario, right? You can't use common sense when you get to this level of math. You have to use math, right? And let the math tell you what the correct answer is. Don't use your own experience or intuition. It doesn't work. You haven't been around long enough for that to work. So 1.00001 and then raise it to the 100,000th power. You still get 2.71 again. This time it's 2.7182. Actually 83 if I'm following rounding rules. Well, I think I can basically stop now, right? I've seen 2.71, 2.71, 2.71 every single time. It will never get larger than 2.71. That is your ceiling. Yeah. So this graph, as x goes to infinity, there is a ceiling. Yeah, in which the graph will never, ever, ever breach that ceiling. It stays always underneath this ceiling. And that ceiling is approximately 2.7182818828, so on and so forth. It goes on forever and ever and ever. Never-ending, non-terminating decimal called E. This is what we call the natural exponential. For practical purposes, if you're just wanting to understand the material, you just want to have a quick way of remembering it, typically most people just memorize the first two digits. 2.71. Yeah. Just like pi, right? Ever since you were, what, 9 or 10 years old, you probably knew that pi was 3.14, right? You might not have known why, you might not have known how, you might not, but you still memorized it since, 5th grade or something. Well, now, this is the new, well, I don't want to call it the new pi, but this is our natural exponential base that we will call E. For all practical purposes in this class, we're really not going to use pi in this class. We're going to use E. Yeah, 2.71 is our natural exponential base. In this particular chapter, I'm just going to graph it. I'm going to write it out. We're not actually going to do anything with it. But in a couple days, certainly by the end of the week, we'll be solving problems that are natural in their nature and typically use this base as their exponent. For today, let's just play around with it. Do some examples, draw the graphs, things like that. So example 3. 4. I think I'm up to 4 now. Example 4. I almost put a 3 there. Example 4, f of x is 5e to the x. Evaluate f of negative 2, f of negative 1, f of 0, f of 1, and f of 2. I hope you all see where I'm going with this, right? I'm creating the mother table here. In this particular example, I'm multiplying everybody by 5. But I'm first going to do the mother function. This is what we call the natural mother function. The natural mother function. Okay, so we're going to plug in -2 for x. 5e to the -2. I recommend identifying the button on your calculator so that you can type in e nicely. It's typically located right about here. Look for the ln. It's usually above the ln key. Use the shift or the second function button, depending on what kind of calculator you have. On my calculator, I have a second function. So you're going to go -2. Do that first. In my calculator, do everything backwards. Hopefully at this point, you've gotten used to how your calculator works. Then you're going to do e, yeah, and then you're going to multiply by 5. And then round it to 4 decimal places, 0.6767. And just march down the row and calculate all these values. You kind of know where I'm going with this. We're going to draw the graph in a minute. So let's 5e to the -1. So again, clear it out. Find your e button. -1, e to the -1, and then multiply it by 5. You have to do it in the right order. Multiplying by 5 would be the last thing that you do. So that's going to be 1.8394. The only one you don't need your calculator for is the 0. And you don't need decimals. That comes out to be exactly 5. Same rules apply as in the last example. If you plug in 0, you're going to get out 1, and then 5 times 1 is 5. Although, you know what? I've seen people do it on their calculator and get it wrong. All right? They'll end up getting 0 or 1 or something like that. The answer is 5. So for that one, I recommend not using your calculator. All right, the rest of these, back to the calculator. 5e to the first. I should point out that the E button does not work unless you have an input. So you have to put 1 on your screen and then hit your E button. I don't want you sitting there hitting the E button going, it's not doing anything, it's not doing anything. Well, you got to put something in if you want it to do something, right? So e to the first and then times 5. And you're going to get 13.5914. I would just use this exercise as an exercise in using your calculator. I'm not going to really make these ones very complicated. These are just meant so that everybody in the class knows how their calculator works. If we were back on campus, I'd do a lab assignment. I'd be walking around making sure that every one of you know how to use your calculator. But I'm going to have to do that virtually. So if you need me, bring your calculator to lab tomorrow or to office hours, and I'll walk you through it. For the last one, you got e squared, and then times 5. You're going to get 36.9453. All of these values are the y values on the graph. So I just calculated 5 different y values on the graph. The inputs were the x values. Okay. So we can draw the graph. It's with all these decimals, it's not going to be pretty. So we'll probably just approximate what these look like. Let me show you how I would do that. I would just go like this. Put my x-axis all the way at the bottom of my graph paper. You don't have to get all of them to fit. Just get a couple of them. So 1, 2, 3, 4, 5. Yeah, that's 0, 5. That's this point here. X is 0, Y is 5. And then see if you can get another one to fit. Let's see. 6, 7, 8, 9, 10, 11, 12, 13. Now let's put it on this side. So there's 5, there's 13. X was 1. Yeah, so down here, X is 1. So I'm over 1 unit to the right. And then up 13 and a half. So just somewhere between 13 and 14. Again, you don't have to be very precise. As long as it's between 13 and 14, it should get marked right. And then there's your graph. I know, it's going to be a pain with all these decimals, but as long as you can get 2 points to be close, that's good enough for me. In fact, one of them will be exact. It's always going to be the one that's a whole number or an integer. And then the rest of them would all be decimals. I can't fit 36 on my graph. So if it doesn't fit, omit. Yeah. And then over here, if you really want to see the rest of these, this is 1.8. So that's right about here. I guess now I have to... And 1.8 is just a little bit below 2. And I'm not even going to try the 0.67. I'm going to omit that also. If I had a bigger graph paper or a more fine grain of grid, then you could probably get more decimal values to fit. You get a couple free answers on here. The domain and the range. Well, I should say you get one free answer. Let me correct myself. The domain is a free answer. I mean, everything's free if you know it, but this is one that you should just memorize for 6.1 and 6.2. Anytime I ask for the domain in these first two sections, it's always negative infinity to infinity. The range is not necessarily free. Make sure you look at the graph carefully. And you're going to get 0 to infinity. The range is the y values. The y values are going up to infinity. And there's an asymptote, horizontal asymptote. I'm just going to abbreviate horizon. Asymptote y equals 0. So this graph will never cross the floor. It has a floor at y equals 0. All right, so that's your first look at the natural exponential function. This one has been multiplied by 5. And that's what stretched out these y values and made them so much larger than the other y values that we had in the past. Let's try another one. So graph this function, find the horizontal asymptote, the domain and the range. All right. A couple of these answers are free. In fact, you can find them right now. The horizontal asymptote is the same as the vertical shift. So you might as well answer that now. So that's your horizontal asymptote. Y equals 9. The last example did not have a vertical shift. It was in the original position. On the x-axis was y equals 0. So you didn't see it last time, but this time it's clear. Yeah, you have a vertical shift plus 9. A second free answer is the domain. So I'll give you a couple of these answers for free. The only one that's not free is the range. So you're going to wait until you're done with the graph. And then don't forget to come back and answer whatever the range happens to be. All right, let's get into this. So we're going to use the mother function. The mother function is y equals e to the x, ignoring everything except the base. That's your MOM. It's actually called the natural mother. As opposed to the unnatural mother. I always use the same x's. -2, -1, 0, 1, and 2. Pretty predictable in this section. Yeah, if you want to use other values, you certainly are free to do that. But if you want your work to match what I've been doing, I recommend using the same x's that I use. I should mention, though, x is called a free variable. You are free to choose any x you want. Yeah, but just because you can, I don't recommend it. Stick with me, kid, and we'll be okay. All right, so now we need to figure out our y values. Just use your calculator to figure out all these y values. You should have an e to the x button. In my last example, I was multiplying them all by 5. This time I'm going to multiply them by -2. Maybe to make it a little more clear in this example. This is example 5. In this example, I will wait to multiply the -2 until I've filled out the mother table, okay? So I'm going to get 0.1353. 4 decimals is fine. For -1, I already did -2. -1, I get 0.3679. Again, I'm doing all these on my calculator. The only one that you don't need your calculator for is the 0. It's going to be 1. Although you could do it. Yeah. Try it. 0, E button, boom, you get 1. Yeah, see? So you don't have to believe me, believe the calculator. E to the 1, that's going to be 2.7183, I guess, if we're rounding. And then E squared is going to be 7.3891. Again, don't expect to get nice numbers here. This is nature, yeah? Nature doesn't give you nice, clean numbers like 1, 2, 3, you know? It gives you 0.1353 and 0.3679 and things like that. All right, so that's your mother table. Let's get into it and find the transformations. If you didn't learn these in Chapter 3, you're definitely going to know them by the end of Chapter 6, or they'll be hell to pay, okay, if you don't know these in the next 2 weeks. I am teaching this class again in the summer, so hopefully I don't have to see you in summer school. Multiply everybody by -2. If that's not enough, I'm teaching it again in the fall. So you've got lots of opportunities if this doesn't get it. Remember, you multiply your scalar and your reflector first. And you do your vertical shift last. And then we send it through the transformation. You might want to look and make sure that the x values haven't been transformed. Look at the x values. Nope. If you see any pluses or minuses, additions and subtractions, then you would likewise affect the x values. But in this particular example, there is no horizontal transformation. That's nice. That means your x values just stay the traditional -2, -1, 0, 1, and 2. The y values are going to be all over the place. I recommend using the calculator. So you got 0.1353 times -2 plus 9. These first couple values should be pretty close to 9. Yeah. Remember last time, a couple examples ago, we were talking about how these have a tendency to get close to the asymptote. So these should all be sort of close to 9. 0.3679 times -2, and then plus 9. Again, I get a number that's kind of close to 9. It's 8 point something. It's getting closer and closer to 9. If I had a giant grid, with hundreds of rows, I would get 8.7, 8.8, 8.9, 8.99, 8.99999. You would literally see it approaching 9. For my table, you just have to imagine that it's getting close to 9. 8.7 is pretty close. This middle row, you don't need a calculator for. That one's just going to be 7. Yeah. -2 plus 9. You can do it on the calculator if you really want, but you don't have to. How about this one? 2.7183 times -2. And then times -2, and then plus 9. 3.5634. And then the last one, 7.3891 times -2 plus 9, -5.7782. Typical form of a natural exponential is that you get one nice point, and then the rest of them are horrible. So definitely plot the nice point, and then you're just going to have to take your chances with one of these decimals and try to get it to stick. If you get frustrated, don't spend 3 hours on a problem. Just email me, and if it's close, I'll mark it right. I don't want you like, oh, I keep getting close to 5.3 and it just won't stick. That's fine. If it's 5.4 and it's not exactly the right thing, I don't care. It has to be in what we call the right ballpark. All right, let's go for it. Let's get this done. I'll break my graphing board while I'm at it. Here we go. All right. Let's see. 0.7. That should be okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Put your asymptote first. So you have a horizontal asymptote at 9. We call that the HA for short. And then definitely graph the 7, because that's a nice point. 0, 7. And now take your chances with one of these other points. How about this one? That's pretty much 3.5. Yeah. And I made the homework problems and the test problems so that as long as you're close to 3.5, it should mark it right. So x is 1, and then there's 3.5. So there's 4, there's 3. Make sure you're at the right 3.5. Remember, there's another 3.5 down here. All right, don't stick it there because that's x is 3.5. We want y is 3.5. And so that's good enough. That's all you need. 2 points, and the graph will stick. Okay. Now you can answer the rest of the questions. So we have the horizontal asymptote. We already had the domain. The domain was that free answer earlier. Negative infinity to infinity. Look here for the range. Just look at the graph. What direction is it going? It's going down to negative infinity. So the range is from negative infinity all the way to the horizontal asymptote, which is 9. It never touches, so I don't want to see any closed brackets. These should all be open parentheses. All right, well, that ought to do it. 6.2 is done in the books. Tomorrow we'll move on to 6.3. Bye.